You know how sometimes you look at a problem and it seems just impossibly complicated, but then you find out it was actually something simple, just in a really clever disguise? Well, today we're going to unmask one of those disguises, right from the world of math.
Okay, take a look at this equation. At first glance, it's kind of a mess, isn't it? You've got your x squared, your y squared, but the real troublemaker here, the part that's creating this whole disguise, is that xy term, smack in the middle. That's the thing that twists and tilts the whole graph, making it so hard to recognize. So, that's the big question for us today. What simple, familiar shape, something straight out of high school geometry, is hiding behind that messy xy term? We're going to figure it out together. And to do that, we need to grab a couple of really powerful tools from our toolkit.
All right, our first tool is probably the most intuitive one, because sometimes to see something clearly, you don't have to change the thing you're looking at, you just have to change where you're standing.
This is called translation of axes, which, yeah, sounds a little fancy, but just imagine you're in a museum trying to look at a painting, but you're way off to the side. What do? You just take a few steps over, right? To a new spot where it looks perfect. That's exactly what we're doing here mathematically. We're just moving our point of reference, our origin, to a better, more convenient location. And how do we describe that little sidestep with math? With these really simple formulas. They let us translate every single point from our old coordinates, the x and y, to our new ones, x prime and y prime, all based on our new, improved viewpoint. Pretty straightforward, right? But what if the painting itself is hanging crooked on the wall? Just moving side to side isn't going to fix that. For a problem like that, we need our second and even more powerful tool.
And this is the core idea behind rotation of axes. Instead of stepping to a new spot, you just tilt your head, and suddenly that crooked painting looks perfectly straight because you've aligned your perspective with it. We can do the exact same thing with our graphs.
So how do we capture that head tilt mathematically? With these formulas right here. Now, I know they look a little more involved than the last ones, but all they're really doing is describing every point from the perspective of a brand new set of axes that have been rotated by some angle theta. This, right here, is the key that's going to let us finally tackle that pesky xy term. Okay, our toolbox is ready. We've got translation for shifting our view and rotation for tilting it. So let's head back to our mystery equation and put these things to work. But here's the million-dollar question, isn't it? We can rotate by any angle we want, but there has to be one perfect, magic angle that will make that whole troublesome xy term just vanish. So how on earth do we find it? Well, the good news is we don't have to guess. Math gives us the answer. See, the entire goal is to make the coefficient of that new x prime y prime term equal to 0. And as this math shows, if we set that new coefficient to 0, we can actually work backward to figure out the exact angle we need.
And this brilliant little formula is the result. This is the key to the lock. It tells us the exact angle theta we need to rotate by to make that xy term completely disappear. And it's based on the numbers from our original messy equation. No guesswork at all. Just pure precision. So let's try it. Let's plug the numbers from our specific problem into the formula. When we do that, we find out that the tangent of 2 times our magic angle is the square root of 3. A little bit of trig later and voila, the perfect angle we're looking for is exactly 30 degrees. And now for the transformation itself. We take our original equation and we substitute our rotation formulas using that magic 30-degree angle. Now at first it looks even messier, I know, but then something amazing happens. All those complicated terms that have an xy tilde in them, they perfectly cancel each other out. They just poof, they're gone. So after the dust settles, what are we left with? What was that simple shape that was hiding in plain sight this whole time? Let's take a look. Just look at that difference. On the left, you've got the original equation with that complicated, ugly xy term. And on the right, after we applied our 30-degree rotation, we get this beautiful, simple, clean equation. I mean, this just perfectly shows the power of changing your perspective.
And what is that shape? It's a hyperbola. It's something we all recognize. It was right there the whole time, just tilted by 30 degrees. All we had to do was tilt our viewpoint to unmask it.
And you know, this is way more than just a neat math trick. This whole idea of picking the right coordinate system is absolutely fundamental. Physicists do this all the time to analyze forces. Engineers use it to understand stress on beams. And hey, Every single time you rotate an object in a video game or some 3D modeling software, these are the exact equations working behind the scenes. It's all about making complexity manageable.
So it kind of leaves you with a final thought, doesn't it? If a simple rotation can turn a confusing equation into a familiar shape, well, how many other problems out there, in science, in art, even in our own lives, are just simple ideas that we happen to be looking at from the wrong angle? Change your perspective, and you just might solve the puzzle. Thanks for joining me.